Hello friends, let me show you how to solve this problem. You find the voltage across the point A and B using Norton's theorem. Okay, so how to solve this kind of problem? So if you don't know the Norton's theorem, how to apply that, let me show you here. So first step, so as we need to find the voltage across A and B, so that's why we're gonna remove this the resistance between these 2 points. We're going to remove this and we're going to make it short. Okay, we're going to make it short circuit. Okay, so let me take a new slide to explain this. So here is the circuit. So let me remove this resistance and make it short circuit. So it's and current flows through it, suppose IN. Okay, now here we're gonna apply KVL, Kirchhoff's voltage law. Okay, so let me make this figure large. Okay, so so IN. So let me take this one as first loop, this is second loop, and this is third loop. Okay, now let's suppose current in this mesh or loop is suppose I1, then this current must be splitting into two directions, so let it be I2, and that's why in this direction current will be I1 minus I2, right? Okay, and then again this I2 current in this direction, let it be IN, so then in this direction it will be I2 minus IN. Okay, that's how we solve. So we're gonna choose a path to apply the KVL. Let me take this path similarly in this mesh also and here also. Okay, now first let me tell you the sign convention that I'm gonna use in this okay, because different in different books different sign conventions are used to apply the KVL, Kirchhoff's voltage law. So when here I'm gonna choose such a way that if the part that I have taken, this part I'm talking about, this part is in the direction of current, then we're gonna consider negative voltage. Okay, then in case of if it is in opposite direction of the current, then we're going to consider positive voltage. Similarly, this is the battery. If the path is from the higher to lower potential, then we're going to take this suppose it is 25 volt battery, then we're going to take this minus 25 volt. And if the path is this is the battery, if the path is from lower to higher potential, then we're going to take this is positive, right? So hope you have understood this. That's going to be the sign convention. Okay, and here you see just wait, let me cut these things. Okay, so in loop 1 or first loop apply KVL, Kirchhoff's voltage law. So here you see this path is from lower to higher potential that I have taken in red color, lower to higher potential. In that case we're going to consider potential gain, so positive 25 volt. Then this current is in this direction, and there is no resistance here, so we're going to ignore this. Now here you see this current I1 minus I2, it passed through this resistance 20 ohm. So here this path I have taken is in the same direction with the current, so here I1 minus I2, this is the current, into resistance, that is 20 ohm, that's going to give you the voltage. And when the direction of the path is in the same direction with the current, then I have already mentioned that I'm going to take this as negative, right? And total voltage in this closed path must be 0 according to KVL, right? So hope you have understood this. So if we simplify this, then what we're gonna get? Then we're gonna get I1 minus I2 is equal to minus 25 by minus 20. That's gonna give you so hope you have understood this. I have shift this to other side, then divided by 20. So that's how we have got. And if you cancel this, then what you're gonna get? Just wait. Then 5 5 is 25, 5 4 is 20. So that's what you're gonna have. So you're gonna have 5 by 4, right? This is suppose equation number 1. This is suppose equation number 1. Okay, now let us take the second loop. Again apply the KVL. Here you see, so this is the part we have taken. Then through this resistance, I2 current passing through this resistance. So 25 into I2. Here this direction of this current is in the same direction with the path that we have taken here. Hope you can see this direction and this direction same. So we're gonna take this as negative, as I have already mentioned earlier, that if the direction of current through a resistance is same as the direction of the path that I have taken, then I'm going to consider voltage is negative. So then again through this resistance, here you can see I2 minus IN current is passing through this resistance, right? So and in the same direction with the path. So here also voltage is going to be taken as negative, I2 minus IN into 10 ohm, because current into resistance, that's gonna give voltage, right, according to Ohm's law. Then again you see this resistance, this part is in opposite direction with this current I2 minus I1. So voltage across this 20 ohm resistance will be taken as positive, right, because the direction of current and the path we have taken is opposite. These two parts are opposite now. I1 minus I2 into 20, okay, and total that's going to be 0. So hope you have understood this. Now you see that this is equal to 5 by 4, so we can replace this by 5 by 4, right? So if we do so, then what we're gonna have, just let me repeat this line again. So here you see, so what we're gonna do, we're gonna replace this I1 minus I2 by its value from equation number 1, that is 5 by 4, that is 5 by 4, right? That's what we're gonna have. Now if we simplify this, here we're gonna get 5, right? So using 1, right? Then our equation gonna be equal to minus 25 I2 minus I2 minus IN into 10. And one more thing, I have also missed this battery here. This is from higher to lower potential, so that's why voltage drop. So that's why we're gonna consider this as negative. Sorry, I missed that one. So minus 100 volt. So here also I have to put this minus 100 volt, right? Then plus 25, then minus 100 volt is equal to 0, right? That's what we're gonna have. Okay, now what we are going to, okay, let it be suppose equation number 2. Now let us take this loop, third loop. Okay, let me take a new slide and let me write the equation number 1, 2 and okay, whatever we're gonna get after, deal with this third loop. So let me write this equation 1 here, and let me copy this equation number 2 as well. This is equation number 2, okay, and so let me take the diagram again. So these are the two questions. Now let me go back to the previous slide. Okay, so take the screenshot of this. So I'm gonna apply the third law. I will erase these things. Okay, take the screenshot of this. Okay, now you see, just because I need the diagram, so that's why I have to do it here. Okay, so now let us apply the KVL in third loop. Here you see, again consider this resistance 10 into current I2 minus IN. Okay, so now you see the direction of the current through this resistance is opposite to the path we have taken, right? So that's why it's gonna be taken as positive, right? And here you see this path is from this shorter to the longer bar of this battery symbol. That means it is lower to higher potential, negative to positive. So in that case, potential gain, so we're gonna keep it positive 100 volt, right? So now you see okay, that's it. These are the two things we have, one battery and resistance, and total voltage is equal to 0, right? This is equation number 3. Okay, now what were the equation number 1 and 2? Let me write here, sorry. So these are the equations number 1 and 2. Let me cut it and let me paste here. These are the two equations, right? So now let me add equation number 1 and 2 and 3. If we add equation number 2 and 3, then what you gonna have? Okay, just let me do one thing. Let me take a new slide. Okay, it will be better if I take a new slide. Okay, this is equation number 3, and let me write the equation number 1 and 2 as well. So these are the equation number 1 and 2. Okay, this is equation number 3. Okay, now you see, if we add equation number 2 and equation number 3, then what we're gonna get? You can see this is positive 100, this is negative 100. These two will be cancelled on adding, right? And similarly here you see minus n2 minus I2 minus in into 10. Here it is plus 10 into I2 minus in. These two will be also cancelled, right? Then we're gonna left with minus 25 I2 plus 25 is equal to 0. So if that is the case, then I2 gonna be equal to 1, right? If you simplify this, you will get 1, right? Minus 25 I2 equal to minus 25 cancels, gives 1, right? 1 ampere. That's what we have got, right? So now let me put this I2 here, putting I2 is equal to 1 ampere in equation number 3. If we put that in equation number 3, then what we're gonna get? We're gonna get 10 into 1 ampere minus in plus 100 is equal to 0. That's what we're gonna get, right? So 1 minus in, that's gonna be equal to minus 100 divided by 10. That's gonna give you minus 10, and this implies, let me write here, this implies minus in is equal to minus 10 minus 1. So minus in, that's gonna be minus 11. That means in is equal to 11 ampere. That's what we have got. So we have got the Norton current, right? So we have got the Norton current. Now let me go back to the previous slide. So now let me erase these 3 equations that we have obtained here. Okay, So what we have got Norton current, that is 11 ampere we have got, right? Here you see this is the Norton current. So now you see, let me make the Norton circuit here. Then first also we need to find the equivalent resistance, that's gonna be Norton resistance here, Rn. So here you see, first let me tell you one more, let me clean this. Okay, first here you see, here how to obtain the equivalent resistance. Here in this first loop, here the resistance is 20 ohm, then this whole thing is in series with this. Okay, right, and equivalent of these two is in parallel with this 10 ohm, right? We're gonna take that way, right? So here you see, concentrate here. So this part is series with this, and the combination of these two is in parallel with this. Okay, so you have to consider when as soon as you get such kind of problem diagram, then you have to take this one with this one as in series, and this whole thing into in parallel with this, right? Remember that pattern. Okay, that's it. So in that case, first, so the equivalent resistance of these two, that's going to be 25 plus 20, as they are in series. So that is 45, right? That is 45 ohm, and this is in parallel with this. So that's why 1 by 45 plus 1 by 10, that's going to be 1 by Rn, right? That's going to be 1 by Rn. So Rn going to be 1 by this, right? Hope you have understood this. Now let's simplify this simply. That's going to be, LCM is 90, so 2 times here, it's going to be 9 times, so 90 divided by 11, right? So that is the Rn we have got. Okay, now if you divide 90 by 11, you're gonna get approximately 8.2 ohm, right? We have it. Now you see, let me make the Norton circuit here. Okay, here you see, now here we have, this is the point AB across which we need to find the voltage. Okay, so here you see, we have replaced the resistance here by we have connected to make it short circuit. So what was there was an resistance 5 ohm. Okay, so we have to draw the resistance here. This is the 5 ohm that we used to say load resistance, right? So now here is the Rn that we have got now. Okay, and the current, Norton current source is here, this is In. So this is the equivalent Norton circuit. And so first, in order to find the this is load resistance, in order to find the voltage across the load resistance, that means between A and B, we need to find the load current IL. So IL, load current through it, IL, that is given by IL is given by Rn divided by Rn plus this RL, Rn plus RL into In. Okay, remember this formula, into In. So if we put the values, then what we're going to have, 8.2 by 8.2 plus 5, so that's going to be 13.2, right? Let me write directly here, 13.2. okay, into In we have got 11. Okay, so if you calculate this, you're going to get approximately 6.83. ampere. Okay, now we need to find a voltage. Okay, and according to Ohm's law, V is equal to, here we're gonna get IL into RL, right? So IL is 6.83 and RL is 5. Okay, this must volt, and that's going to be equal to approximately 34.15 volt, right? So hope you have understood this. Thank you for watching. See you in the next video. Bye bye.